All right, guys, so this is chapter 1 of Force and Motion, which is our second unit in 8th grade science. This chapter is all about motion, speed, velocity, acceleration. We're going to talk about displacement versus distance and scalar versus vector units of measurement for motion. So we're going to start with speed. Now, if you remember our anchor phenomena, when I introduced that in class, was what would it take for the Millennium Falcon to jump to light speed, right? Star Wars theme unit. And to do that, we're gonna have to figure out what the speed of light is, right? We're gonna have to really delve into that question. We're gonna have to understand what it actually means. So, how fast is the speed of light? I'll wrap this story up quickly. I know you don't want to spend too much time on this, so let's do it. So essentially, the first question was: is light infinite or finite? Meaning, is it something we can measure, or is it an infinitely, big number? Like, is it like pi, or is it just like 3.14? You know what I mean? Is it 3.1486, blah, 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 whatever it is? Or is it just 3.14? Is it an exact number? Or is it something that's infinite? We'll never ever measure it. So Galileo was the first guy to really investigate this. What he did was he stood at the top of a hill and he had his assistant stand at the other top of the hill. And they were like 5 kilometers apart. And they tried to time how long it would take the light to be seen from the other side, from the other hill, by the assistant or by Galileo. So they were trying to time the light, how fast light would travel over 5 kilometers. They thought that, that's long enough distance. There's no way it'll be that difficult. Well, it's too fast for them to actually tell whether it travels instantaneously or it has a finite distance. So the next guy that really made a big discovery was Ole Romer. And essentially what he did was he timed how long it would take Jupiter to be seen from the Earth, how long the light from Jupiter would travel. And what he did is he did it around the eclipse of the moon around Jupiter and around the sun, the Earth around the sun. So there's a certain point where Jupiter can't be seen based on the position of the moon or based on the position of the Earth or on the other side of the sun. What he did is he timed essentially how long before it's supposed to show up and how long till when it shows up. It's about a 20-minute difference. So that means the light from Jupiter took 20 minutes to travel to Earth in that particular rotation. Now, so what they did there is they took the distance from Jupiter, how far is Earth away from Jupiter, and how long did it take to be seen. So they came up with, I think Jupiter's like 385 million miles away or something like that, divided by 22 minutes. And or maybe it was like 500 million at the time, because Jupiter fluctuates between 365, 600 million or something like that miles away. And what they came up with is 300, or no, it was about 220,000 kilometers away, because we get closer to 300 once we go to this stuff. So that was like our big first discovery. Oh, okay, it's finite, we can measure it, this is about what it is. The next thing was James Bradley. James Bradley measured how long it took for us to see stars depending upon their change in placement. So like this, if you look up at the sky, you'll see a star, but it's not actually where you think it is. That's just how long it took. Like where you see it, it's actually already moved, because stars move around. They move in little circles and the Earth turns, right? The Earth rotates around the sun. Well, by the time you see a star, it's already moved its location. So if you look up there in the sky, stars aren't where you actually think they are. That's where they are based on how long it took you to see them, because the light has to travel a certain speed. So what he did is he predicted the motion of the stars and where they're at versus where they're actually at, and then the distance away from them. And he got closer to 300,000. I think he got like 299,000 kilometers away. So he's pretty close. And then ultimately, when James Maxwell discovered electromagnetic radiation, we kind of figured out, oh, okay, so light's a form of electromagnetic radiation, and it's about 300,000 kilometers per second is how fast it travels. So that's roughly how all electromagnetic radiation travels. That's about how fast. So that's kind of the story in a nutshell. There's a lot of great videos on YouTube you could watch to learn more about this. But essentially, speed is a measurement of distance over time, miles per hour, meters per second, kilometers per hour. And the speed of light is just the distance light travels in a unit of time. That's what the speed of light is. So we can measure it in multiple different ways. So units of speed, we're always going to need a distance, and we're always going to need a time. So some units of distance or length is meters, kilometers, centimeters, foot, feet, yards, miles, things like that. Time, seconds, hours, minutes, years, months, milliseconds. Those are some common units of time. Now, we mainly use meters per second, sometimes kilometers per second or kilometers per hour, but we usually always stay in the metric system, and we'll always be dealing with seconds, hours, or minutes. So that's something to note. So let's look at an example of measuring speed. So if we are to look at example 1, we're going to find the average speed of Usain Bolt during his world record setting run in 2009. So he runs 100 meters and he does it in 9.58 seconds. Fastest ever, right? If you were to average his speed over the course of that run, you would find that he ran 10.44 meters for every second he ran. Okay, so that's how we get to 100 meters. That doesn't mean to say that he ran 10.44 the whole time, right? He did start at 0 because he started out the beginning of the line, but over the course of the run, he did run 10.44 meters per second. Why is this important? This is important because we're going to look at two different types of speed, instantaneous speed and average speed. So if instantaneous speed is like when a cop tracks you on their radar gun, right? Traveling 65 and a 45. That's instantaneous speed. You were going 65 miles per hour at that very second he tracked you. Average speed is the average speed traveled over a certain distance or certain time. So speed can be taken averaged or it can be taken instantaneously. If you want to know the average speed, you got to have the total distance and the total time. If you want to know the instantaneous speed, you have to have something to track that instantaneously. Or you can cut up an average trip into instantaneous sections. And I'll do that right now. Here's example number 2. So if you were to break up Usain Bolt's 100-meter run into different sections, let's say that 0 to 20, 20 to 40, 40 to 60, 60 to 80, 80 to 100, you would find his fastest point was during the 60 to 80 meter mark during his world record setting run. It's the fastest anyone's ever run during a 100-meter race. So his average speed from the 60 meter mark to the 80 meter mark was 12.42 meters per second. So this is closer to an instantaneous speed. Is it tracked with a radar gun? No. But it's the closest we're going to get in an example like this. We do have radar guns. We might do some of that. But ultimately, we're going to look at a lot of average speeds. And then we might find an overall average. So that is all I got for you today. Instantaneous speed, average speed. We're not going to focus on the speed of light too much. Those two terms, definitely important. And then the equation. Speed is equal to distance over time. And then we'll look at the speed triangle. Super useful stuff. We'll come back to you next time. All right, guys. Here we go.